Hello, my name is Uziel Hernandez. This is the Bioengineering 159 Extra Credit project, and I will be talking about the effectiveness of benign prostate hyperplasia surgery, and just a little bit of background of what benign prostate hyperplasia is. Benign prostate, or we'll just call it BPH, is actually a condition in which there is prostate enlargement. This creates a problem because it actually narrows the urethra, the urethra pathway, and it also constricts the bladder. It doesn't allow it to have its full its full volume, and so that can be a problem in terms of physiology. And so I just wanted to talk a little bit about how I took on this problem, and in the paper they actually show some of the conditions, and they give some parameters and how they went about it. And I just I was able to model the problem that they had stated. And so here we go. The paper talked about the bladder being in its healthy condition and its compromised condition. And so here I modeled a bladder. The COMSOL has a tool where you can actually model geometry, and I created a circle to simulate the bladder. Also some cylinders, or triangles, or I'm sorry, rectangles right here to simulate the entrance point of the of the urine, and then the urethra. And so here we have a healthy one. This is how it normally should look, and you can you can use the different parameters to model the flow. But also I was able to create the geometry for a compromised bladder, which pretty much has the right here, it's the plays. If you can kind of imagine the uh, the prostate right here, being enlarged as opposed to normal right here. It actually obstructs and it narrows this pathway, and you can see that it actually hinders flow. And this is the flow right here, red being highest flow, and then the blue being not very much flow. And so that's kind of how it goes. I decided to focus on the urethra particularly, which it's the exit point, and to see what really goes on in there. I just created excuse me, a 3D model on how to do that. Once you have the geometry, it's not very difficult. COMSOL would just do it. There's a way to do it 3D. And so it's not very difficult to do in terms of making it a 3D, but you just have to have their geometry right with the right parameters, and whatever it is that you're looking for. And so I wish I could show you the COMSOL, more of the COMSOL, but I unfortunately I'm using a Mac computer that doesn't have COMSOL, so I had to do this in a different computer. But I took screenshots of my results, and I'll just explain along the way how to do it in COMSOL. But to be very specific, we would need a different video to just go through all the COMSOL. But I'll just explain the equations that I used and the parameters that I used. And with that, someone who has enough experience with COMSOL can figure out how to do this. And so I used the Navier-Stokes equation for laminar flow, and then it's COMSOL has a built-in tool where you can actually use Navier-Stokes and just change the parameters that you need. And so I won't get too much into detail due to time, but this is the actual the formula that simulates flow. And so that's what I used. Oops. Oh shoot, what did it do? Alright, that was weird. Okay, alright, sorry about that. So okay, so there's the parameters of a healthy a healthy urethra, inlet of 8 millimeters, outlet of 1 millimeter. There's the Young's modulus, the healthy Poisson's ratio, and that's all from the papers parameters they give you. Then there is a velocity profile. Once you input all the properties that you want your urethra to have, or whatever you're modeling, then it just gives you the option of modeling of what actually would happen. And so here's the velocity, and here's the pressure profile, and as you can see, it tells you different pressures, different times, and different velocity. And so right here, it's a simulation that you can do. It's pretty cool, actually. It shows the bulging of the urethra, and it's pretty cool. So it actually moves and stuff. And the parameters of a person who has this condition are also modeled, and so the outlet is still inlet 8 millimeters, 1 millimeters. The Young's modulus, however, it's a bit changed because of the because of the condition, and the Poisson's ratio remains the same, and the density of urea and viscosity remain the same. And you can see right here that there's a lot more stress, a lot more red in the actual hindered urethra. And so that just there's just more stress, and there is actually more stress on the just on the urethra and on the tissue itself. After that, you can do after the surgery, there is an increase in availability of flow. And so the surgery is supposed to remove the deceased prostate. And so the Young's modulus changes is a it's a bit, it actually the tissue is softer, so it has to change, and the Poisson's ratio remains the same. But here we can see that there is an increased volume. I mean, you can see that there's more space right here. And so here you have the different pressure. You can see there's much less pressure than the first one. And so you can see how there's also not as much red, and so there's less stress, less bulging out, and that's all simulated in COMSOL. And so this is just a little bit more of what I was able to calculate, that the paper had. And then this is the effectiveness, and you can read a little bit more on the paper. But here are the results. 25% effectiveness. They talk about the increase in flow and the decrease in stress, and so that's about it. The conclusion that showed that obviously, I mean, the operation is better because it actually just reduces the reduces the stress. And so sorry about that. And but yeah, skip all this. Okay, all right, well, thank you for watching. I'm having a bit of trouble here, but thank you for watching, and that was my presentation. Have a good day.